بعمل شير بقى كده هم هيشوفوا دي. Hello, dear students of the third secondary. Today we'd like to continue talking about digital electronics. Last time we talked about the transistor and how the transistor is used in the electric circuit. And we said that the transistor, we have two types of the transistor. We have PNP and we have NPN. And we said that the transistor is different from any other electronic component as it has 3 terminals instead of 2. Today we'd like to talk further about how we connect transistor in the circuit. And actually we have 2 major ways of connecting transistor in the electric circuit. And each one of them will have some consequences of the circuit. So the first type of connection is called the common base connection. From the name, common base means, we said before that the transistor has 3 parts, the emitter, the collector, and the base. So when I say common base means that I will have the base. Common means between 2 different sources. So if you look at here the diagram, here the transistor has 3 terminals, the emitter, which is this part, the collector, which is the right part here, and the base, which is this one down. So how many sources of electric current we have here? We have 2 batteries. We have this one and we have that one. So when I say common base, as you see here, the base, which is this line, is connected here to 2 batteries. So one connection with this battery and the other connection with the other battery. So I have the base between 2 batteries. So that's what we say, that's why we say it's common base connection. VEB, which is the voltage between the emitter and the base, is called VEB. The voltage between base and collector is called VCB. And let's now investigate how it's connected. Pay attention, here is the current passing from the positive up there, as you see the IB, towards this way, and then coming this all way again to the negative. So the base has being connected to the positive pole of this battery, so that the current will go as indicated in the arrow here, and then here, and then here. We call this kind of connection forward. So the E and B, the emitter and the base, they are connected in the forward way, while the other circuit, which is the base and the collector, in the reverse way. What we mean by the reverse way is the positive with positive pole of the battery and the negative with the negative pole of the battery. So here I have forward connection and here I have reverse connection. And only in this way I will have common base doing what I want, which is magnifying the electric power. Pay attention, it's not magnification of the current, it's not magnification of the signal, but it is only magnification of the work, of the power, the magnification of the power. So the method of connection is E and B, the emitter and the base. We connect them forward connection, the collector and base reverse connection. But how it works? Last time we explained how this works. The emitter is called the emitter because it emits electrons or releases electrons. And these electrons, they wander about in the base for a short period of time, and then they are picked up by a collector. Now, the reason the emitter current is always bigger than the collector current, as we said, that the emitter is the source of the electrons. And that's why, because part of the electrons are consumed in filling some of the holes in the base, because the base is p-type. So that's why the two currents are not actually the same. They are not equivalent to each other because electrons, they are released from the emitter. Some of them, they are consumed in the base, and the rest will be the current passing in the collector. So the collector current is less than the emitter current, because the transistor in this case does not amplify the current. It cannot be used to magnify the electric current in this way. And why is this? Because always I have the current of the emitter bigger than the current in the collector. And that's why the transistor cannot be used in this way to magnify the electric current, but rather it will be used to magnify the electric power. So here the function, and I put it in bold, the function of common base connection of the transistor is to magnify the electric power, not the current, magnify the electric power. Here we have some expression which is important. It's alpha E, the current division. What we mean by the current division is the ratio between the current of the collector to the current of the emitter, which is simply the ratio between the output current to the input current released from the emitter. But this has to be done at constant potential difference between the base and the collector. Actually, the potential difference has to be constant between the common thing and the collector. So alpha E, the current division, equals the current of the collector divided by the current of the emitter at constant VBC. What we mean by VBC, voltage between the base and the collector. So alpha E is the current division, and this current division is near to 1. We said before that the current received by the collector is not actually 100% the current released by the emitter because of the consumption of some currents in the base. But this consumption is actually very, very small, and practically we can put the ratio IC to IE equivalent to 1. We can put it approximately equal to 1. And that's because the base is very thin, so only very small ratio of the current is consumed to fill the holes in the base. So I can say that the current of the emitter is nearly equal to the current of the collector. Okay, that's why the ratio will be practically equal to 1. Another way of connection of the transistor is the common emitter. Before, in the previous diagram, we said that the base can be common between the collector and the emitter. In this way, different type of connecting the transistor is using the emitter as a common. So in this way, we put it. The method of connection will be the E and B will be forward connection, like before, but the C will be connected to the positive pole of the battery, and the emitter will be connected to the negative pole of the battery. Now, in this case, when I connected the collector to the positive pole of the battery and the emitter to the negative pole of the battery, and I put the emitter in between, the transistor will function in a different way. So how it works when it is connected in this style? Electrons of the emitter repel with the two batteries. Why is this? Because negative repels the negative, positive repels the positive. And because of this, electrons of the emitter repel with the two batteries. Electron current is collected at the emitter and moved toward the collector. Now, in this case, if a small current is added to the base current, very small current, I added a small current, what happened is the collector current will be magnified. And this is called the action of the transistor. So action of the transistor is simply using the transistor when I connect it in common emitter in such a way that C will be connected, the collector will be connected to the positive pole of the battery, and the emitter will be connected to the negative pole of the battery. And as a result, I will have a reverse. This reverse connection will force the the current from the electrons to be collected at the emitter and to move toward the collector. So in this case, I actually adjusted the transistor. I adjusted it so that I can pass a small current to the base, and what happened is the collector current will be magnified. So for this, I call this the action of the transistor is magnification of the current or magnification of the electric signal. Now we have important expression here which is called the current gain. Before we talked about the current division, which is the ratio between the output relative to the input. But the current gain is here I put because the base is no longer the base is no longer common, it's the emitter which is common. So the base here will be the input, and the collector as before is the output. So the current gain will be beta E equals IC, which is the current of the collector, divided by IB, which is the current of the base. And this has to be done at constant voltage between the emitter and the collector. So beta E is called the current gain, which is the ratio between the output current, which is the current of the collector, relative to the current of the base, because the base here will be the input. So beta E equals IC divided by IB at constant voltage between the emitter and collector. Pay attention here, I always put the division at constant voltage between the common and the collector. The common here is the emitter. Before it was the base, but here it is the emitter. So I say beta sub E is the current gain, which is the ratio between the currents of the collector relative to the currents of the base at constant voltage between emitter and collector. All right, it is the same idea but different name. Now, how can we calculate the current gain in terms of current division? Now, don't be confused between current division and current gain. They are not the same, but we'd like here to calculate the current gain using the current division. All right, so we are going now to use algebra to restate, put a different formula of the current gain, and instead of expressing it in the form of current of collector and base, we would like to express the current gain in terms of current division. And this is very useful when I use it for practical purposes, and also useful when I solve problems. Before, now we are going to use algebra, the alpha E, which is the current division. As we know, that it's the ratio between the current of the collector divided by the current of the emitter. From here, this is pure algebra now. IC equal alpha E multiplied by IE. What did I do here? Cross multiplication. I did not invent anything. I just cross multiplied the equation. IC here equals alpha E multiplied by IE. So here IC, the current of the collector, equals alpha E, the current division, multiplied by the current passing in the emitter. Before we said that when I connect the transistor in common base, we said that the current of the emitter will be the sum of the current passing in the base plus the current passing in the collector. So IE equals IC plus IB. Now, using algebra again, I want to get IB in one side. So IB here in one side equals IE minus IC. What did I do here? Pure algebra. I did not invent something new. It's just pure algebra. I reverse it, the IC the other side with negative sign. so that I have IB in one side, which is IB here equals IE minus IC, okay? I put here the IC and I highlighted it with the yellow, and I highlighted this one also with yellow, so I can use this and this, okay? So IB equals IE minus, I replace this part, which is IC, okay? I replace this one IC. I put it between brackets here because I'm going to replace it. So IB equals IE minus, what's IC from here? It is alpha E multiplied by the current of the emitter, IE. So I replace the IC by its value from here. Now IB will be equal to IE minus alpha E IE. What did I do? Nothing. I just removed the brackets. Remove the brackets and I will have IB equals IE minus alpha E IE. Now, we said before that alpha E is equal to IC divided by IE. And also we said that IC from before equals alpha E IE. Where did I get IC from? From here. Remember? From this equation. I put it here. Now, can I use these two things, all right? Alpha E value and the IC value. Can I use them to get IB, which is the current of the base? Sure. Just replace one by one. So the IB equal IE. I put it as it is, IB equal IE minus. Here I have alpha E IE, alpha E IE, right? Now, beta E, the current gain, equal IC divided by IB, as we said before. If we substitute for the current of the collector and the current of the base, I will have the formula I want. So what I do here is beta E equals alpha E over 1 minus alpha E. What did I do here? Pure algebra. So how to do it? Substitute for the current of the collector, the IC. From where I got the IC? From here. From this equation. I substitute for IC. And I put its value here. And then I substitute also for IB, which is the denominator. So when I substitute for IB from here as IB equals IE minus alpha EIE, when I put these two and use algebra, I will have beta E equals the final formula, which is beta E equals alpha E over 1 minus alpha E. So I ended up having now two things only, the current gain beta E and the current division alpha E. And all the other currents are not in the equation, which is very useful. Now, the final thing is I explained or I expressed the current gain in terms of current division. And I did not use any other terminology. So beta E equals alpha E over 1 minus alpha E. Okay, so this is very useful because I can get the current gain with only one step if I know the current division, and vice versa. So I don't need to calculate many things. Now, after knowing the two ways of connecting transistor and the advantage of each one of them and the uses and how the electric circuit is drawn, now we'd like to mention some of the uses of transistor when connected in common emitter. Now, when I use the transistor in common emitter, I have actually two things to use. I can use the transistor in this way as a current amplifier to amplify the signal, or I can use the transistor as a switch. So let's investigate the two advantages of using the transistor in common emitter connection. So The first one, as we said, the current amplifier. I use the transistor as a current amplifier, and this is very useful. So if a small current is added to the base current, the collector current will be magnified. What does it mean? Suppose, for example, I have now the current base is actually very small. If I added a small current base to the original one, the impact of this small addition of the current in the base will be huge in the collector, which means that the gain will be higher. I will have the electric current or the electric signal magnified or magnified. Okay, and this is what we call the action of the transistor. I can also use the transistor as a switch. How to use it as a switch? Consider the base now as an input and the collector is the output. And what about the emitter? The emitter is no longer an input. The emitter now is the common part. So the base is the input and the collector is the output. I will call the input voltage, which is the voltage of the base, Vn. Vn means the input. Okay? Input voltage is the voltage of the base. And I will call the output voltage, which is the voltage of the collector, V out. So I have Vin and have V out. So what is the idea of using the transistor as a switch? The transistor acts in the reverse way, such that when the input voltage which is the base voltage, is large, the output voltage will be small, and vice versa. So again, Vin and V out, they are actually opposite to each other. And they are opposites in such a way expressed in the diagram that I will explain later on. So this diagram shows how it is done. But before this, we need to make sure that we have some terminology clear. VCC is the battery voltage. VCC is the battery voltage. VCE is the potential difference between collector and the emitter. IC is the current of the collector, and the RC is the resistance of the circuit. I mean by this any kind of resistance, ohmic resistance, traditional one. So when I use it as a switch, as we see here, I have Vn, which is the voltage input voltage, and here I have V out, which is the output voltage. Okay. So, and the emitter here is the common part. How to know it's the common? As you see here, it is connected in between this sub-circuit and this sub-circuit. So it's as if I have two circuits attached to each other, and the emitter is common between them. The first one is the input circuit, which is this one, as I pass here from this part to that part. All right, this is the input circuit. And the other one is the output circuit, which I put here, the output circuit. And what's common between the two of them is the emitter. So, as you see here, if I would like to use the transistor as a switch, and this switch I would like it to be on. On means closed, the current can pass. Now, if I would like to do such thing, I have to connect the NPN transistor in that this particular way. If you look here, now this is the base is connected to the positive, all right, and the emitter is connected to the negative. So the emitter to the negative here of that battery, and also to the negative of the other battery. As you see here, the emitter, which is the common part, is actually connected to the negative here and the negative here. And as a result of this, the transistor will work as a switch which is working or closed, so the current will pass. Now, watch out here, I will indicate how the current passes. This is the positive, so the current will go all the way, and then this is the IB, I mean, the current of the base going this way and follows this way with the direction of the arrow down here and back again to the negative of the battery. Now, how about the other one? Here is the positive also. So the current goes this way, up, and then to the left, and then goes down here, and then with the arrow back again to the negative pole of the battery. So in this case, I have the transistor acting as a switch which is closed. So I can actually use it instead of using a normal switch, which is very useful sometimes in electronic devices. All right, so this is the circuit when I use the transistor, NPN transistor with common emitter as a switch, and in this case, the switch is on and the current can pass. Now, how about the same way if I would like this, the transistor to work as a switch, and this switch will be off? Off means the current is not allowed to pass. What do I mean by this? The current cannot pass in the base. Again, what does it mean to have a transistor as a switch? Is to allow the current to pass or to prevent the current from passing. Passing where? In the base circuit, in the input circuit. All right. So if the transistor is connected in that way, watch out here, this is the base, and it's connected to the negative pole of the battery. It's not the positive. Will this make a difference? Oh, yeah, it will make all the difference, because reversing the polarity of the battery here will transfer the transistor from a switch on into a switch off. Now, and I will tell you why. If you watch here, the polarity of the battery is reversed. The base is connected to the negative pole of the battery, and the emitter here is connected to the positive here and the negative here. Now, changing the polarity here will cause the current to pass in that direction. Watch out. I go here, yes, down, 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 and then to the left, and then up again. Watch out here, the current will have to go in that direction, and watch, the arrow should be coming against it. So when the current is coming against it, it means that the current will not pass. So in this case, the current will stop, because it's supposed to move the other way around. Again, positive, down, up again, and when it's going here, it is now actually opposite to the original current, which is supposed to be going on. So in this case, the current will not pass in the base circuit. If the current does not pass in the base circuit, which means that the current will stop. When the current stops, it means the switch is off or the circuit is open. So the circuit in this case is actually open circuit, which means that the current is not allowed to pass in this position. All right, so here is the summary of what's going on if we use the transistor as switch on and switch off. The transistor acts as closed or switch on, or acts as open or switch off. How to switch on and off? Now, only reversing the polarity of the battery, connecting the base and the emitter. So by reversing the polarity, I will control if it will work as switch on or switch off. Now, when connecting the base with a positive, or this is the now explanation of the mechanism of how it works. Now, when connecting the base with the positive or the large voltage, what happens? And it will work as switch on. Now, if I would like it to work in the opposite way, which is to be a switch off, or to not allow the current to pass, I will connect the base with the negative or a small voltage. What happens? The input Vn, or the voltage between base and emitter, is large. This is how it works as switch on. If the input voltage or the voltage between base and emitter is small, the opposite will happen. It will not work, or it will not allow the current to pass. And why is this? Because the battery voltage, which is VCC, equals the voltage of the output voltage, V out, plus the IC/RC. What's IC? The current passing in the collector. And what's RC? The ohmic resistance in the collector. So the battery voltage is actually the sum of the voltage of the output plus IC/RC. And because of this, when I have the output different in such a way that the primary voltage will be small output, the IC has to be large, all right? So when this is small, to keep the battery voltage the same, this part has to be large. And because RC is actually constant and I cannot change it much, what actually changes here is the current in the collector. So I will have large current in the collector, all right? This is if it works as a switch on. What if I would like it to work as a switch off? I will use the same formula. The voltage, the battery voltage will be equal to VCE, okay, plus ICRC. I did not make any change. The formula here is the same like the formula here, all right? Now, but what happened here is I will have a large output, all right? So here the output will be large. And as a consequence, when the output is large, what will happen automatically? The current of the collector will be small to keep the voltage of the battery constant, all right? So when one goes up, the other one goes down. So when the transistor is working as a switch on, ICRC will be large. When it's working as a switch off, ICRC will be small. Consequently, as a result of this, the current of the collector will be large here when it's on. The current of the collector will be small here when the switch is off. And this is always because the output is small when it works as a switch on, and the output is large when it works as a switch off. Since the input Vn or VBE is large, what happened? The voltage out will be small. All right. Now the opposite will happen if I have the inputs here small. If the input is small, it will work as switch off. All right. So what is the result of all of this comparison? The result is the base current flows when the switch is on. The base current will not flow when it is works as a switch off. All right. So it's all how we allow the base current pass or not. If it passes, the transistor works as a switch on. If it does not pass or is not allowing the current of the base to flow, it will work as a switch off. All right. This is a simple comparison of the mechanism of how it works as a switch on and switch off. And as we said here that the Vin and Vout, they are actually opposite to each other, or when one goes up, the other one goes down. The relationship between them is explained in this diagram. Here is the Vn, all right, the independent variable here, the x-axis. And when I change the voltage, the input voltage, and I will pick up what happens in the output voltage, I will realize that they are actually moving opposite to each other. So when the Vn, the input voltage is, which is the base voltage, is large, what happened? The output voltage will be small, and vice versa. All right. So they are opposite to each other. When one goes up, the other one goes down. All right. Now, by this we finish everything like related to the transistor and how it works and how it's connected in the circuit and why and the advantage and all of this. Let's now generalize everything, because now transistor is studied because it's a key component of digital electronics, and actually the very important part of many other electronic devices, if not all of them. So they are found everywhere. Now, to generalize now things about the electronics, we have actually two types of circuits. We have analog circuit and we have digital circuit. If I have normal circuits, I call it analog circuits. In the analog circuit, it's a normal one. I have connection of many components, but when I have digital electronics or digital signal, the situation changes. Now, to differentiate or to compare between the analog and digital electronics, let's consider this diagram. If I represent here the signal as a wave, moving with time, within time frame. As you see here, the signal goes up and then down and then up again and then down, as we said. But if you look carefully, the wave is not actually geometrically symmetrical, which means that I don't have geometry in it. And why is this? Because it's analog. It's actually analog, which is subjected to noises with interference and other things. And this is actually what happened when we listen to analog signal, just like a normal radio. We have noise and we have confusion sometimes, or interference between more than one voice. And this is because the signal is not pure. You have many other signals with it, with the original one, and that's why it's not clear. So what is actually analog electronics? Analog electronics is when I have anything like sound, image, or any other device or anything, I convert the physical quantity, such as sound or light, into continuous electric signal. And this continuous electric signal can take any value of the decimal number, all right? So it can be anything. It's not discrete, it's not distinctive, it is not peculiar. It's just like a random collection of electric signals, and we put them together and we end up having analog electronics, or the normal outputs that we hear sometimes in the radio with many confusion and noise. But actually it is useful because applications of analog electronics are everywhere, such as the normal microphone. Now, the normal microphone is converting the sound into electric signal so that I can magnify the sound. Video camera, the normal video camera, also depends on analog, which is converting the light into electric signal. Television is using also the same kind of analog, the normal television. The television, in the transmitter, you have like sound will be converted into electric signal, and then electric signal will be converted into electromagnetic waves. The image is also converted into electric signal, and then from electric signal will be converted into electromagnetic signal, so that sound and light can fly or transmit over large, huge distances. And then at the receiver, they will be picked up by antenna or aerial. So the antenna will pick up the electromagnetic waves, transfer, and then change it or convert the electromagnetic waves into electric signals. And the electric signals will be converted to sound and light. So 3 different applications of analog electronics. But the story is different when they talk about the digital electronics. Now, in digital electronics, I don't have all values of decimal number. So in digital electronics, I have physical quantity. I converted the physical quantities into discrete code. What do we mean by discrete? It means that it's not random, and it is very peculiar and distinctive. It has distinctive start, distinctive end. We call this discrete code. And this discrete code based on only 2 values. So I don't have all possible values of the decimal, no, but I rather have 2 values only. It's either 0 or 1. So digital electronics is simply converting the physical quantities into discrete code based on only 2 values, 0 or 1. Everything can be either 1 or 0. 1 means high, 0 means low. So if you look here, if I have to convert the previous signal into digital electronic signal, I will have discrete. As you see here, it is either 0 or 1. Nothing in between. I don't have something going up and then going down. No, no. I just have discrete values. This one, that one, that one. They are discrete. So if I look here, 0, then 1, then 0, then 1, 0. All this part, 0. And then I have all this part, 1, 0, 1. All this 0, and then 1, 0, 1. As you see here, I have only two values, 0 and 1, and that's why the digital electronic is very discrete, and the voice will be, or the sound will be very clear, and the image also will be very clear because of this. I have actually many applications of digital electronics. We just pick up some of them. At transmitter, the normal analog electric signal is converted to digital signal using analog to digital converter. So what is ADC? ADC stands for analog, D stands for digital, C stands for converter. So analog to digital converter, ADC. At the transmitter, I have normal analog electric signal, which is the normal one picked up by a microphone or by camera, will be converted into digital using the ADC. Then at the receiver, the other end, I would like now to pick up this digital signal and then convert it back again into normal analog electric signal so that I can listen to the voice, or I can listen to the sound and watch or see the image. And this is done the opposite, which is converting between the digital signal into the normal analog signal using the DAC. So DAC, which is D digital, A analog, C converter. So I use the digital to analog converter to do the opposite action, which is to pick up the digital signal, transfer it into analog signal using the DAC. Another example of using digital electronics, which is images can be converted to small units. Instead of having like the normal camera, I can have now digital camera. What's the idea of the digital camera? Is converting the small units. The image will be converted, or will be like separated into small units. Each one of them is called pixel. So I have many pixels, and then I can change the pixels into binary code. Binary code depends on two numbers, 0 and 1. So digital image is simply changes the image into pixels, and then change the pixels into binary code based on 0 and 1. Also, I can use the digital electronics in storing information on disks, like how the information is stored on the computer. So the computer is using the two ways, which is magnetization technique. Now, when you magnetize in a certain direction, it's like 0. When you magnetize it in the opposite direction, it would be 1. So I use the direction of magnetization as an indication of the code, which is either 0 or 1. So in computer, I have the storage of storing information in the form of 0 and 1 based on the direction of magnetization. All right? If it's magnetized in a certain way or a certain direction, I call it 0. And if it takes the opposite way, I call it 1. All right? By this week, we finished all the analog and digital electronics. Let's now talk a little bit about the binary one, which is 0 and 1. One very important part is how to convert between decimal to binary. And this is very, very simple. We will not go into too much hard examples. We just have a simple one. The idea is extremely simple, and the technique is very, very simple, how to convert between binary and decimal, from decimal to binary, and from binary to decimal. The decimal, as we said, has a base 10. All right, that's why it's called decimal. Decimal number like 1, 2, 3, 4, and 10. This is called decimal. But binary is explaining the number in a different way. I have only two things, 0 and 1. So how I use two things only to write all the numbers in the world? So I can use it in a certain technique. Now, let's now talk about how to convert decimal to binary. Imagine now that I have this in this example, a solved problem. He says the number 20 will be what as binary? If I write 20, I would like to see how the computer will write it as 0 and 1. So the technique is simple. I start from right to left so that I don't have to reverse. So I start from right to left. 20 divided by 2 equal 10. Sorry, I write here it's 10. All right. So it's 2 minutes. Like 10. 20 divided by 2 equal 10. All right. And the rest or the remainder is 0. And I take the 10 here. 10 divided by 2 equal 5. And the remainder is 0. Means that I don't have anything left. Then I use 5 divided by 2. 5 divided by 2 equal 2. And the remainder is 1. And then the last one, 2 divided by 2 equal 1. And the remainder is 0. And at the end, I have 1 divided by 2 equals 0. And I put 1 here. So in this case, I have just to put the remainder here, 0, 0, 1, 0, 1. Here, 0, 0, 1, 0, 1. So the final answer is 20 decimal will be equivalent to 1, 0, 1, 0, 0 in binary. And I can put it between brackets and I put 2 as sub. And the last question is how to convert the binary into decimal. This is the binary, it's 00101. And if I would like to convert this binary into decimal, I just write the number as it is. And then down, I put 2 because it's the base I have. And I start here from right to left. To the power 0, to the power 1, to the power 2, to the power 3, to the power 4. Okay? Now, if this is 0, I put nothing here. 0, I put nothing here. This is 1. So 2 power 2 equal 4. I put it. 2 power 3 equal, because multiplied by 0 equal nothing. 2 to the power 4 equals 16. And because it's multiplied by 1, I put it. So I have here only 4 and 16. 4 plus 16 equal 20. And this is how to explain the binary into decimal. So the binary 1, 0, 1, 0, 0 is equivalent to 20 in decimal. All right. So this is how, as you see here, the result is the same. This is the technique of how to convert the binary to decimal and decimal to binary. By this, we'll come to the end of our session for today. Thank you for listening. Don't forget to drop any question that you have. Good luck, inshallah. We are almost finished the whole unit. And as you said, if you have any question, you can ask the question online, or you can come and visit at school. And thank you for listening. My name is Ahmad, and I teach physics. Next time, inshallah.